Continuing on with factoring polynomials, we're going to learn some methods to actually take those long polynomials and factor them into their pieces. If you remember, when we factor things, we're trying to find out the zeros or the roots, and that's where the polynomial crosses the x-axis. So as funny as the polynomial is going to look, it crosses the x-axis at a few different spots, and that's what we're solving for. So factoring higher degree polynomials is very similar to factoring quadratic equations. Ax squared plus bx plus c. We would always factor those into two sets of binomials. There's three ways we're going to do it. Factoring by grouping, and then two special methods which are the sum of two cubes and the difference of two cubes. Jumping right in. Okay, I have a higher order polynomial. This one is called factoring by grouping. We take that higher order polynomial and group the first two terms together plus the second two terms together. We look at each group and find the GCF. So between x cubed minus x squared, the GCF is x squared. If I take an x squared out of just this binomial, I get x minus 1. If I distributed that back, I'd get x cubed minus x squared. Same thing. Next, I'm going to look at this binomial and factor out the GCF. I always want to factor out the negative if it's leading. So I've got 25 in common here. So I factor out a negative 25. I'm left with x minus 1. The goal here is for the binomials that are left, for them to be the same exact. I've underlined them in purple, x minus 1 and x minus 1. So we're actually going to look at this whole piece and factor out the common binomial. Take both of these, I'm going to factor them out and write them right there. Okay, so both of those got factored out, written right there, and I'm left with x squared minus 25. So factors of this polynomial are x minus 1 and x squared minus 25. But this is the difference of two squares. So I wrote that again, and this binomial breaks into x plus 5, x minus 5. This is my final answer. Let's review. First, I group the first two terms and the second two terms with a plus in between. I take those first two terms and I factor out my greatest common factor. Take the second two terms and I factor out the greatest common factor, making sure I bring the negative with me. I'm left with two binomials that are the same. I'm going to take those and factor them out. And I'm left with x squared minus 25. X squared minus 25 is the difference of two squares, and I'm left with my answer. We're going to try two more of those. All right, big polynomial. Parentheses around the first two terms plus parentheses around the second two terms. GCF is x squared. What's left over is x minus 2. GCF is negative 9. What's left over is x minus 2. This and this will always be the same thing if you're doing it right. Factor out your matching binomial and write down what's left. So I have x minus 2 and the difference of two squares. That's not a coincidence. So I get x minus 2, x plus 3, x minus 3. And that is your final answer. One more example, and by this point you should be seeing a pattern. Big polynomial. Parentheses around the first two, parentheses around the second two. Factor out your GCF, and you're left with 2x plus 1. Factor out your GCF, which is a positive 4, and you're left with 2x plus 1. Matching binomial, and what you're left with. Here I don't have the difference of perfect squares, and that's okay. You have your final answer. Okay, let's try those difference of cubes and sum of cubes. Special rules. So the sum of two cubes, here's your basic form, a squared plus b squared. This always factors into a plus b times a squared minus ab plus b squared. Ignore that for a second. Let's look at the difference. I should have written difference of 2 cubes right there. A squared, a cubed minus b cubed. Difference, 2 cubes. Sum, 2 cubes. We get a minus b, a squared plus ab plus b squared. Very basic example. Sum 2 cubes. This is a cube. 3 times 3 is 9, times 3 is 27. So if I break this up into x cubed plus 3 cubed, we have our a and our b, a and b. We get x plus 3, x squared minus 3x plus 9, a squared minus ab plus b squared, a squared minus ab plus b squared. Difference, 2 cubes. 8x cubed is the same as 2x raised to the third power. 2 times 2 is 4, times 2 is 8. Minus y cubed. So we have a and b. A minus b. A squared plus ab plus b squared. They're always going to work out like that. Our goal here is to find out what is a, what is b. So you have a difference of 2 cubes. We have to figure out what is a, what is b. Factor the expression. Sum. Is this a cube? Is that a cube? No, but we have a GCF that we can factor out. Greatest common factor is going to be 4x, and I'm left with an x cubed plus 27. Sum of 2 cubes. X cubed, 27 is the same as 3 cubed, so we have our a and our b. Write the 4x down. It's just one of those things that we have to hold on to till the end to write our final answer. A plus b, a squared minus ab plus b squared. Okay? It's just like the example on the last slide. Let's try another one. 125d cubed minus 8. Difference, 2 cubes. Okay? 125 is the same as 5d cubed. 5 times 5 is 25, times 5 is 125. So a, b. A minus b, 5d minus 2, a squared plus ab plus b squared. 2 more examples. Okay, whoops. Sum of 2 cubes. That doesn't look like a cube, but amazingly it is. 8 breaks down into 2 cubed. Z to the 6th. We have to remember our powers of powers. We get z squared raised to the third power because 2 times 3 is 6. A plus b, a squared minus ab plus b squared. Last example. 2x to the 5th minus 16x squared. Subtraction, 2 cubes. They don't look like cubes, but you can factor out a GCF to get them to look like cubes. Our GCF is 2x squared. Okay, that's the smallest amount of x's, so I'm going to factor it out, and they're both even. And I get, look, difference 2 cubes. A is x, b is 2. One of those things you just have to write down at the end. A minus b, a squared plus ab plus b squared. So our goal here is to get everything to look like the sum or the difference of cubes and go with the formulas and get your answer. Thanks.